So today we'll be tackling an angular momentum problem using a merry-go-round. The question reads, a 20 kilogram child is sitting on the edge of a 200 kilogram merry-go-round with a radius of 5 meters while it is spinning at a rate of 3.7 revolutions per minute. If the child moves to the center, how fast will it, the merry-go-round, be spinning? First thing you always want to do on these problems is illustrate what you know. So right now we'll do a rough rendition of a merry-go-round. Center and a radius 5 meters. Child on the outside weighing 20 kilograms. Let's record to the side what we know. The mass of the merry-go-round is 200 kilograms. The mass of the child is 20 kilograms, and the W, or the revolutions per minute of the merry-go-round, angular speed, would be 3.7 revolutions per minute. Now, we know that we can solve this using a conservation of momentum problem, so let's go ahead and write out the formula that we'll be using. U initial equals IW final. Also, we know that a merry-go-round will classify as a disk and the child will classify as a point mass. So why don't we go ahead and break up this conservation of momentum formula into the separate components that will make it easier to solve in the end. So we know that for a disk, we'll be using 1/2 mr squared times W initial plus, and the point mass will be mr squared times W initial equals, obviously, 1/2 mr squared times W final, and this will be the final of the merry-go-round plus the final of the point mass. So again, mr squared times W final. Now we can begin to plug in numbers that we know into the variables that are already set out. So we know that the mass of the merry-go-round is 200 kilograms and its radius is 5. We also know that its initial revolutions per minute is 3.7. As for the point mass, we know that the mass is 20 kilograms and that the radius is the same as the merry-go-round initially, which will be 5. Also, we know that its revolutions per minute are the same as the merry-go-round initially at 3.7. On the other side of the equation, the merry-go-round will stay the same with its mass, obviously, at 200. Its radius will stay the same at 5. And its revolutions per minute, which is what we will be looking for, will be put in as the variable W. The point mass will stay the same in regards to mass at 20 kilograms. Its radius, however, changes to 0. Therefore, this last equation can be eliminated. Let's tackle the first part of this equation by doing some simple multiplication with these numbers, just to make it a little bit more simple on ourselves. When you multiply 200 by 5 squared, divide it by 2, and then multiply it by 3.7, you should get the number 9,250. As for this point mass, when you multiply 20 by 5 squared and then multiply that by 3.7, you should come out to 1,850. On the other side of the equation, we will multiply 1/2 by 200 by 5 squared and leave the variable in there. So we'll come out to 2,500. It's 2,500 and leave the variable W in there. Obviously, this part of the equation will go to 0 since you're multiplying by 0. So we'll just go ahead and leave that out. Now it's just a matter of simple algebra. So let's go ahead and add 9,250 by 1,850, which will come out to 11,100. Set that equal to 2,500 W as above. And now we will divide 11,100 by 2,500, and you should get the answer 4.44. So now there will be no conversions necessary since the W is already given to us as revolutions per minute. So we can leave it as that. And your speed of the merry-go-round in the end will be 4.44 revolutions per minute.